So chapter 5 was the work energy theorem, and then also conservation of energy. That's like the roller coaster problem, an object moving up and down. In chapter 6, we had momentum. We had the idea of impulse, and as it relates to forces, F equals delta P over delta T. Remember, impulse, that is our delta P. I is just equal to delta P. And then we also had the conservation of momentum. And that comes into play when we have objects that are colliding against one another, and we can figure out, if we know the velocity of 3 of the objects, we can figure out the velocity of that 4th object. And then that's all for 5 and 6. In chapter 7, we're going to have just a bit of introductory stuff about angles, and I'll sort of recap the entire chapter here. It just takes a few minutes. Has some introductory stuff about angles. We'll see rotational kinematics. The angles, by the way, is going to be like converting units and sort of knowing your unit circle. That's stuff that you probably know already. Kinematics will be applying the rotational kinematics equations. That's just like our V equals V naught plus AT, X equals V naught T plus 1/2 AT squared, just like chapter 2, except we're going to be applying them in slightly different situations. And then finally, centripetal acceleration. If you're in the lab, you've seen centripetal acceleration. Unfortunately, we didn't get to it in class before the lab was just because of
this last week.
I know, right? But usually we do that, but you know, it's just we had to restructure all of our labs because of the pandemic. So those are the 3 big ideas in chapter 7, and that's the totality of the exam coming next week. Keep those big ideas in your head as you move forward. All right, so in chapter 7, I'm going to go to the end of the book. There's a blank page there, and then we'll come back and work some problems. End of the chapter, rather. That's a page, if you're looking, page 149. So in the chapter, first, just looking at angles. Remember angles, kinematics, and centripetal acceleration. We're looking at angles. Remember the units that we use for measuring angles. The SI unit is a radian. And, well, not 1 radian, sorry. The SI unit is the radian, and 2 pi radians is equal to 1 revolution, is equal to 360 degrees. So those are the angles that we'll use. But the SI unit, you'll never go wrong converting everything to radians, but your SI unit is going to be in radians. You'll have some conversion problems. We'll look at some like that in some of the old tests today. Second, we have kinematics. And as we move from chapter 7 and then into chapter 8, we'll see actually in chapters 7 and 8 everything that we've done so far. We'll see kinematics, Newton's second law, energy, momentum. We'll see all those things come back again, except now instead of moving in a straight line, we're going to be moving in a circle. A lot of the concepts will still be the same, and the way that you apply them will still be the same. The only thing that's going to be different is that the variables will change. And so begin cementing these in your head right now, that whereas before we had x, now we're going to have theta. Whereas before we had v, now we're going to have the Greek letter omega. And then before we had acceleration, now we have the Greek letter alpha. Let me just write these down. I know that you probably don't speak in Greek very often, but this is theta. That's one that we've used commonly. Don't call this W, call it omega. That's our angular velocity, and then alpha is our angular acceleration. So we'll call this our angular displacement. This is our angular velocity. And then this will be our angular acceleration. We'll have some other variables that will translate into this rotational frame in the next chapter, chapter 8, where we get into energy and momentum and Newton's laws of torques and forces and all that. But for right now, we're just doing kinematics. When we do this exchange in variables, then our kinematics equations, which before were v equals v naught plus at, and x equals v naught t plus 1/2 at squared, these will now become omega equals omega naught plus alpha t, and then theta equals omega naught t plus 1/2 alpha t squared. So these are our kinematics equations. Said it's going to be a lot the same as we did in chapter 2. You'll see it's actually not that complicated once you get into it, into applying them in different situations. Okay? The third thing that we have here is going to be centripetal acceleration. If I have an object that's spinning around in a circle at a constant speed, it still has a changing velocity. So here's one of your balls. This is from chapter, or from the lab that you did. So if I have an object that's spinning around like this, it's moving at a constant speed, but this object is also continuously changing direction. Here, the velocity is in that direction. Here, the velocity is to your left. Here, the velocity is going away from you. And so because I have this changing direction, that means that the velocity is also changing. Because remember, velocity is a vector, and a vector has both a magnitude and a direction. And so far, when we talk about changing velocity, really all that we're talking about is that the speed is going up or down. But when we have something like this, it has a constant speed, but it does have an acceleration. So now we see an object that has an unchanging speed, but the acceleration is non-zero. And anytime I have an acceleration, I also have to have a force. We're going to call that force the centripetal force. In this case, what is the force that's causing this object to go in a circular path? What is providing the force that's causing it to go in a circular path? Right, the tension in the string. So this tension is pulling towards the center of the circle. That's what centripetal means, by the way. Center seeking. So I have this center seeking force that's causing this object to not fly out straight ahead, because that's where the velocity is going right here, but instead to move in this direction and to constantly change its direction. And so we're going to get into centripetal acceleration. The way that we calculate centripetal acceleration, I'm not going to derive it for you, it's sort of a geometric argument, but the way that we calculate the centripetal acceleration is AR. Let's see, do I use R for this? Let's see. Sometimes you use AC for centripetal acceleration, sometimes people use AR. It looks like I used AC. Yeah, so AC for centripetal acceleration is equal to v squared over r, where this is our speed, and this is the radius of the path. All right, so that's our centripetal acceleration. Our centripetal force, then, Fc, is also equal to the mass times the centripetal acceleration, which is equal to mv squared over r. Just substituting that centripetal acceleration here in the Newton's second law to change this, to figure out what force is required to cause this acceleration. Okay? Those were the ideas that you were dealing with in the lab that with the ball going around in a circle. That's it for chapter 7. Let's look at some questions in chapter 7. Let's see what we're good one. Let's try number 2 here. This is in the homework problems in the back of the book. And then we'll move up and do some of the quick tests in the chapter. And then we'll also move back into the old exam. But you can be doing that as well as you prepare for the exam next week. So just like in chapter 2, these problems require you to read it and, know what the different variables are as you read through the problem. So a lot of this is really just being able to read properly, knowing what the values mean. I have a potter's wheel that moves from rest. So the rest, that means that it's initially not moving. So that tells me which of the variables. The initial velocity, which I'm calling omega, right. The Greek letter omega. So omega naught is equal to 0. This is going to be in radians per second. Although, let me say here that whenever we're doing these kinematics problems, you don't have to convert your units from, in this case, revolutions per second to radians per second. So instead of starting this in radians per second, I'm going to say revolutions per second. Now, there are some cases where it matters. But in these kinematics problems, it doesn't matter because you'll see that the units will work out at the end. However, when we get next chapter in the torques, and then later I'll show you when we're doing centripetal acceleration, it matters sometimes if your units are in revolutions or radians. If you're ever, revolution, right? If you're ever in doubt, you'll never go wrong converting to radians. So if you ever have a question, just always convert to radians. And you can use that conversion factor, that 2 pi radians is equal to 1 revolution. All right, so omega naught is 0 revolutions per second. It goes from rest to an angular speed of omega of 0.2 revolutions per second. Sam, you got me all tongue-tied now. And it goes in a time of 30 seconds. T is equal to 30 seconds. And I want to know what is the angular acceleration. What are we calling that? What's the variable? Alpha, right. So I want to know what alpha is. Look, those equations are on your equation sheet. You'll have that for your exam. You'll have it for your quiz. But one of those equations is our velocity equation. Omega equals omega naught plus alpha times t. And so if I want to know alpha, it's pretty simple one-step problem. Alpha is going to equal to omega minus omega naught divided by t. And so that's going to be 0.2 minus 0 divided by t, which is 30. Is 0.007. That's in revolutions per second squared. You'll have a couple problems that are similar to those, where you're either calculating the angular velocity, angular acceleration, or the angular acceleration. Unlike in chapters 2 and 3, you won't have any two-step problems. Most of yours, well, I'll take that back. You could have a two-step problem, like where you have to find one value and then find another value. Okay? But you won't have any substitution problems, where you have 2 equations with 2 unknowns. Not going to do that. You can do it, but it takes too long on an exam. Okay? Let's go up and try one of the quick test questions. I think there was just one. Let's try this one. Notice on this one that there is a change in unit, that everything's given to you in revolutions, but the answer is in radians per second squared. So you can either convert everything right away in the beginning, that might be easier, or you can convert your answer in the end. So on page 144, starts from rest, goes to an angular displacement of 3.2 revolutions in 2 seconds. I want to know its angular acceleration. All right, let's try to wrap up in about 10 seconds. Stop at 220. 220. Just guess if you're not sure. All right. All right, so at this point, you could convert your theta into radians, or you could wait until the end. I'm going to wait until the end. So here I want to know, I've written down what I know. I know that theta is equal to 3.2 revolutions. I know that the time is 2 seconds, that it goes from 0 to 3.2 revolutions in 2 seconds, and that it initially has 0 angular speed. I don't know its final angular speed, but I don't need to know it at this point. All I really need to know is what is the angular acceleration. That's what I'm asking. I know that theta is equal to omega naught t plus 1/2 alpha t squared. And I think I have everything here, right? Omega naught is 0. So this whole term goes to 0. So 3.2 equals half alpha times 2 squared. So alpha then is equal to 3.2 divided by 2, or 1.6. And a lot of you did put D, in fact, but recognize that that is 1.6 revolutions per second squared. So now I need to make an extra step to convert this into radians per second. I know that in 1 revolution, there are 2 pi radians. So that's 1.6 times 2 pi. I think that's 10.1, right? Yeah, so that's equal to 10. Well, it should just be 10 point to keep proper sig figs, or 10.1 radians per second squared. Which I think most of you put, but some of you did put D. So that's why. I'm not sure if you put C. Why you put C. If you put A, probably what you did is you just multiplied 3.2 and 2, which I usually do that too, to make up the wrong answer. But it's very seldom to give you the right answer. You just multiply all the numbers, it doesn't usually work.
I can tell you what I did.
Oh, did you get that? Okay.
Yeah, I got it, but what I did was I knew that omega was revolutions per second,
Uh-huh.
and to find the final, I did 3.2 times 2 pi, and then divided it by the 2 seconds, and I got 10.05, and then divided it by 2 because of the time, because I did omega equals omega naught plus alpha t.
Okay. Okay. Yeah. But that's not exactly right. I understand what you're doing, but yeah.
This makes more sense.
Good. I'm glad.
That's what I did.
Good. Good. Okay. Let's do another one. Let's actually go to the back of the book. You can practice some more of these kinematics questions, and then we'll come back and work the centripetal forces questions. So let's go back, looking at usually exams 3 for this. Sometimes exams 4. Yeah, let's see. This looks like a good one. This is exam 3, fall 16. Let's do number 21. This is the fall 16 exam. are doing a lot better on this one. Let's try to wrap up in about 10 seconds, or about 15 seconds at 2:10. 2:10. Ask your neighbor if you're not sure. See what they put. 5 more seconds. Okay. The radius here is not necessary. In fact, after this problem, there's one other thing that I'll tell you where the radius does become important. We'll look at number 22. So I have a tire that rotates from rest. So that means omega naught is equal to 0. It accelerates at a constant rate. That's alpha is equal to 2 radians per second squared over a 5-second interval. So t is equal to 5 seconds. And then I'm looking for theta. Theta is equal to omega naught t, but omega naught's 0, so that term goes away, plus 1/2 alpha t squared. So it's equal to 0 plus 1/2 of 2 times 5 squared, or 25 radians. Everything was in the radians in radians at the beginning, so the answer is going to be in radians at the end. The answer is C there. Let's look at number 22. One thing that you'll see in the notes, if you haven't seen it already, is that we can translate our rotational quantities into linear quantities. Like, for example, here if I have a tornado, let's imagine that we're looking at the tornado from the top up, that we're standing above the tornado and looking at it. And this tells us that this tornado has a radius of 50 meters. And at one point, the speed of the... Oh, yeah, so the diameter is 50 meters. Thank you. At one point, the speed of the wind is 200 miles per hour. Or meters per second, excuse me. And it wants to know what is its angular velocity in revolutions per second. So this is one of those cases where the units matter, that we need to be in radians per second as we go through the calculation, and then we'll have to change it in revolutions at the end. But these angular and linear quantities are related by this relationship. Theta is equal to, S is equal to theta times r. You've seen this in geometry. I know that you did this. This is the arc of an angle. And if I have a certain angle theta, this distance right here is the distance s. If you make that angle go through a full circle, what is that expression for s? That is, if theta goes through the full circle, it's 2 pi times the radius, right? That's where we get our circumference from this expression, that the arc or the distance is equal to theta times r. And theta must be in radians. Make sure that you're aware of that. And then we have similar expressions for omega and for alpha. That V is equal to omega r. And then A is equal to alpha times r. We can see that the units will work out in this. Omega, for example, is radians per second. And then r is in meters. Radians isn't really a unit so much. Like, it's not a physical unit that has a physical meaning. It just means that I'm moving through this angle. And so when I do something like this, where I multiply radians per second times meters, the radian just goes away. You can sort of think of the radians as sort of like a placeholder. When I multiply them, the radians goes away and it just leaves me with meters per second. Likewise here, the radians would go away and I'm just left with meters, and I'm left with meters per second squared here. So I can translate my linear quantities into angular quantities. So what we do here with this question, well, I'll let you do this actually. What is the angular velocity here in revolutions per second? Recognize that you're going to calculate that in radians per second, so you'll need to convert it into revolutions per second when you get the final answer. And then also I give you the diameter, not the radius.
R is radius, not radians. For the V equals omega R.
Yeah, R is the radius. Right, R is the radius. Radius of your circular path. Let me give you a little nudge in the right direction here. So I'm looking for the angular velocity. I know that V is equal to omega times R, and I'm looking for omega. So omega then is equal to V divided by R. I know V, I know R, which is half of the diameter. 200 divided by 25. Now that's not the answer, right? That would be 200 divided by 25 is what?
8.
8, right. To get the answer, I have to convert that now from radians per second into revolutions per second. Is the right answer there? The right answer is there, right? Okay, let me just work through it. We'll see. I might have made a mistake. I might have changed this to radius in the problem. I don't remember. Anyway, let's figure it out. I'll just leave the clicker base open. So omega is equal to 200 divided by 25. That's equal to 8, but that's in radians per second. This is always going to be in radians per second. To convert that into revolutions, I say 1 revolution is equal to 2 pi radians. And so 8 divided by 2 pi, 4 divided by pi. Yeah, I get 1.3. Is that what y'all got? Yeah. So it should be 1.3
Choice N.
radians per second. That's revolutions per second. Yeah, it's 1.3. Just put E, everybody. E's not the right answer. I'm sorry. I think actually when I gave this test, I changed the word diameter to radius, and then it works out. It gives you 0.64. Okay, yeah, that's what I intended. But just put E right now. Everybody put E. E, E, E. Okay, I'm going to stop this. Oh, man, look at that. Great job. I'm proud of y'all. Hey, why can you never hear a pterodactyl go to the bathroom? Oh, come on. Did y'all really know that one, or have I told it to you before?
We know that one.
Okay. Have I told you the O Street? Yeah. Oh. Huh? The O Street joke? What's the worst thing about living on O Street? You got to walk a whole block to pee. All right, we'll do another middle school joke. So, knock, knock. Smell mop. No. Okay. Let's go back into the chapter, and we're going to do those other quick test problems. We can come back after that and do some more of these.
2020 is a Joker winner. Yeah. 2020 is a joke.
All right, so here I have a ball traveling around in a circular path. You can think of it as going over my head like this, but this is sort of looking down on it. And if I cut the string or if I just let it go at this point, I want to know which path will it follow. Will the ball continue to follow path A, which is the circular path it was traveling in? Will it go out straight in path B? Will it travel outwards, pulled out away from the center, or will it travel straight outwards like that? Which path will this ball travel when you cut the string or you let go of the string? All right, let's stop at 110, 110. Okay, good. B is right. Sort of talked about this earlier, that the centripetal force is what causes the object to move in a circular path. That at this point, the velocity is in this direction. And it's that centripetal force that's actually pulling that velocity to move into the circular path. And if you take this force away, which in this case is the tension in the string, then that object is just going to move off in a straight line. Let's see, I can show you. See if I can do this without hitting anybody.
Oh, no.
All right, so I'm going to try to let it go like when it's right here. And we'll see which path it follows.
No, he's like legit letting go.
Yeah, I'm going to let it go. Y'all ready? Watch your head. It won't hurt if it hits you.
You say that, but.
Whoop. Yeah, so I got it. So when you take away the centripetal force, it's actually going to cause it to move in the same direction that it was moving when that force was taken away. All right, let's try the next one. Okay, so this was a little more complicated. I'm going to help you with it. When I have a car that's going around on a flat curve, like this. If it's a banked curve, it's different. But if the car is going around on a flat curve, there is a force that holds that car onto the road. Otherwise, if it didn't have that force, it would just go in a straight line and go off of the curve. What is the force that holds that car on the road, that actually makes it go into that circular path? The friction, the centripetal force or the friction? By the way, centripetal force isn't really its own force in and of itself. A centripetal force is a force that's already in the system. And then you have to identify it as the centripetal force. Like with the ball and string, the string, or the tension in the string, provided the centripetal force. In this case, it's the friction that is acting on the tires, between the tires and the road, that's providing the centripetal force that causes it to move in a circular path. So when we're thinking about centripetal forces, don't think of it as a separate force, but that you're looking for a force in the system to identify as the centripetal force. Should be easy because the centripetal force is always going to be in which direction? What does centripetal mean? Center seeking. So it's always going to be towards the center of the circle. In this case, the object would tend to move in this direction, so the frictional force is going to be in the opposite direction, opposite the direction of motion. So the frictional force that's holding this truck on the road is going to be F, and it's going to pull it towards the center of the circle. Now, you're saying, oh, but there's a frictional force too that's propelling the truck forward, and that's true. But that's something different. That's not the centripetal force. So I have this frictional force that's actually causing it to go around the circle. And I want to know if it can go around a flat curve with a radius of 120 meters with a speed of 25 meters per second, what maximum speed can it go around a curve having a radius of 75 meters? You'll see similar problems to this in the old test and even in the homework, so you should go back and work them. But let's just first consider this situation where I have 120 meters radius with a speed of 25 meters per second. I know that the frictional force is my centripetal force. And so that frictional force is going to be equal to mass times acceleration, or mv squared over r. Further, I know that the frictional force is mu times the normal force, and the normal force is m times g. Just remind you what I did there. Frictional force I know is mu times the normal force, but because this object is on a flat surface, the normal force is equal to the weight. And so I just write that as mu times m times g. And then this is equal to mv squared over r. So one thing happens here that's curious is that the mass cancels out. So when you're going around a curve and you see those signs that are posted for the safest speed in that curve, that's where those come from, is that they're doing this calculation for the curve, dependent upon the coefficient of friction between your tires and the road, depending on the conditions. Is it icy? Is it wet? Is it dry? And the radius of that curve, how tight is the curve? Is it a really gentle curve or is it a really tight curve? And then also the speed v. Now, if it's banked, it becomes a lot more complicated. And we'll look at, there's some conceptual questions about the banking of curves. The first thing that it does is it changes your normal force, and then it also provides another centripetal force. Let's ask that question, sort of as an aside. If I have a banked curve, let's say that my curve looks like this, and I'm looking at the car right here. No, actually the wheels would be, so this is like the front of the car coming towards you. Here you are in the car. If I have a banked curve, what's acting as the centripetal force in this case? Let's stretch it out to an extreme banked curve, and that's a banked curve that's upright, that's completely upright. You ever go to the fireman's fair? You ever go on that thing that spins you around? Like they put you on this hand with people, and then they put you up against the wall, and then they spin it around. It is a centrifuge, right? But for people. So they put people in the centrifuge. And what provides the centripetal force in that case? What's causing you to move in a circular path? What force? Can you identify the centripetal force in that scenario? No, there's no tension. There's no rope pulling on you. But it's not gravity, because gravity is acting down. I need a force that's acting towards the center of the circle. No? What force? The normal force, right. So when you go in that thing, it feels like it's pushed up against the wall, right? You are. But the reason you feel that is because the wall is pushing back on you. Okay? Have y'all been in one of those?
No.
Has anybody ever thrown up in one of them?
Oh.
Yeah. No, I have not either. So in this case, the normal force provides Fn and the frictional force combined to give you an increased centripetal force. But I'm looking at a flat curve, so it's different. The flat curve, I get mu times g equals v squared over r. And since I know r and I know v, I can calculate mu. I can say that mu is equal to v squared over gr. And so in this case, mu is v squared over gr. It's going to be 25 squared divided by 10 divided by r, which is 120. Then I get a value for mu that's equal to 0.52. Then in the second part, I really want to know what is the maximum speed that I can go around a curve with a radius of 75 meters. So I want to know the maximum speed. V is equal to the square root of mu times g times r. I just solved that for v. And so this is going to be the square root of 0.52 times 10 times 75. 5.2. I get 19.7 or 20 meters per second. So A is the right answer there. You can do that from a different way where you're setting up a ratio of the two quantities. Yeah, why did you have 120? Why did I have 120?
Oh, because the radius is 120.
Where did I have it?
When you had it with GR when you were finding the.
I'm thinking about in the square root.
Right here? I didn't have it. With a 120-meter curve, which is a big curve, I have a maximum speed of 25 meters per second. But then the question is asking, what if my curve is now 75 meters? Yeah, you can go through, by the way. I know a 75-meter curve is a tighter curve, so it should have a bigger or smaller safe velocity. It should have a smaller safe velocity. So whereas this was 25, I can get rid of D and V right away. So it has to be A or C. Okay? Those are probably the more difficult from this chapter, doing those types of problems. And you should spend a little more time on the centripetal force problems. With practice, you'll see there are only really a few types of problems that I did. Yeah. Okay. All right, let's do this last one. Remember how angular and linear quantities are related to one another. How do I relate angular and linear quantities? And then also remember that the angular quantities must be in SI units in order to make that work correctly. All right, let's give about 10 more seconds. I'll stop at 2:30. 2:30? $2:30? Just guess if you're not sure. Okay. So I have this thing moving around at a constant angular speed. But I know that there's an acceleration because it's constantly changing its direction. I know that that acceleration, our centripetal acceleration, is equal to v squared over r. So I know the radius, but I don't know the velocity or the speed of this object. But fortunately, I can find it. I can say that v is equal to omega times r. But in order to use this relationship, I have to have my omega in radians per second. I'm going to do that over here. 5 revolutions per second into radians. In 1 revolution, there are 2 pi radians, so that's 10 pi radians per second. And because I have pi in all my answers, I'm going to leave that pi. So I have v is equal to, I'm sorry, not radians per second. That's right, 10 pi radians per second times the radius, which is 0.1 meters, or just pi. This is in pi meters per second. Now, finding the centripetal acceleration, I have v squared, that's going to be pi squared, divided by the radius, which is 0.1, or 10 pi squared. So the answer is going to be E, which more put than not, but not enough put it in my opinion. I know that the whole pi thing probably trips you up, but that's a common thing in standardized tests. So sort of get used to it, where you keep a variable or a number like pi throughout to the end of the answer. Okay? Oh, are there any more of the? I don't think there were. No. So we'll have our quiz on Monday, and then we'll have more time to review. I'm looking for a help session on Tuesday, so be looking forward to that. Maybe Tuesday, probably at 3. I'll send you an email about that for a moment.
You never give them that. You never give them that.
Well, have a great day, okay? She's not this way. Great.
I always forget.
Chapter 6 for your quiz on Monday. Chapter 6.
I just want to say you scared me a little bit, because you had